put it another way, you can just take it, this W star, we will see the explicit form, that's a stationary solution, and take the symmetric gradient, that's a stationary solution of this equation. So we have already have a stationary solution by looking at this. So what do we have? We proved that for a solution of this system, that's symmetric to tensor HAB, suppose initially the data decays pretty fast in the R direction, and R goes to infinity, then the solution will converge to the following combination. Here we have the Kerr perturbation, the mass perturbation, and the angular momentum, and we have these extra piece C times the deformation tensor of W star. And fortunately, or unfortunately for me personally, actually Hefner, Ince, and Vasi, they have a much complete description of this solution, this system. They prove that suppose that we are looking at the same equation, the harmonic gauge and the linear gravity, and they can do that not only for Schwarzschild but also for Kerr with small angular momentum. The result is following: the solution will converge to this linear combination, the Kerr perturbations, the standard solution we have seen, and there is this 6 extra dimensional stuff. I will explain what they are at the end, but there's no contradiction in the sense that our decay requirement for the initial data is much stronger than theirs. They can allow much weaker initial data, and the result is they can see this extra 6 dimension solution space, and they can do that for the Kerr space time. Okay, so the main analysis tool comes from the study of scalar wave equations. For a scalar wave equation, one look at its stress energy tensor, that's a symmetric to tensor, like that. It has 2 nice properties. First is that the energy condition, if you contract it with 2 future vectors x and y, it's non-negative. Roughly speaking, that's the gradient of psi squared. And the wave equation will tell you the stress energy tensor is divergence free. If you contract it with a vector field, compute divergence, that is what you have. In particular, if you take the heating vectors, this will give you the conservation law. So I want to explain in this one slide what happens in so-called the vector field method initiated by Donformas and Raransky. That's a very robust way to estimate and study the wave equation in black hole spacetimes. So the key is to take a future vector x in a very clever way, and contract it with the stress energy tensor, get one form, JA, then apply the divergence theory. The key task is to make the divergence to be non-negative. To be precise, that will be bounded below by a certain H1 norm of psi. Then from the divergence theory, we have 3 positive boundary terms, one along the horizon. This is the Penrose diagram of Schwarzschild. One along the horizon, one along the future slice, one along the non-infinity. All these 3 together with the bulk is controlled by the initial data. And by using this, and further assume that initially psi decays like r to the minus 1 toward the infinity. Then one can show the energy of psi as some weighted H1 norm along the slice will actually decay like tau to the minus 2. So this is the analytic tool we are going to use. So let's start from the wave equation for one forms. We do the decomposition into 3 pieces, W0, W1, and W2A. A stands for the cylindrical coordinate. So W0 and W1, they are scalars. W2, that's a section of the cylindrical one form. And the wave equation can be rewritten in terms of these 3 quantities. Start with the wave operator with some lower order terms, and we would like to group some of them into these notations P and S. They are first order derivatives of W's, and they have a natural geometric meaning. S is the trace of the deformation tensor of W. Therefore, S is a scalar and satisfies the wave equation we just discussed. And P is the component of the exterior derivative of W. W is one form. Take the exterior derivative. That's a two form. That's the TR component, and it's a scalar. The derivation of it is not zero, but the source term is given by the time derivative of s. Then this is the scheme of proving the theorem W converges to a constant times W star. We started from S, just use the result for scalars, S decays. Then we move to P. P doesn't satisfy the wave equation. S appears on the right hand side, but we already have the control of S. Therefore, P decays. Then we keep playing the same game. We move to the equation of W0, the P term. Now play the rule of the source term, but there's one subtlety. In this case, we cannot argue that W0 converges to zero. We need to subtract the rotationally symmetric part. This is the, we take the average along the spheres, and we need to subtract that part. We denote that by W0 L rather equal to 1. Estimates only apply to this portion, and we can show, well, this part also decay. Then we move to the system of W1 and W2. It also decays up. Still, we need to subtract the rotationally symmetric part, so only the W1 for L greater or equal to 1. And what about the spherical symmetric part of the solution? Well, if you simply set S and P to be 0, one can prove that part is actually stationary. Once it's stationary, the wave equation becomes a second order ODE in the R direction. There are two linear independent solutions, but only one is regular on the horizon. And this is how we found this W star. We just solved the second order ODE. So, and that's the case when S and P vanishes, both vanish. And what we really have is, well, these two quantities decays, and we can show then the rotationally symmetric part converge to this regular stationary solution. So this finishes the proof of the theory. The wave one form converge to a constant times W star. And actually, there's a interesting view of the existence of this W star. If you take the exterior derivative, it becomes a two form. Then it satisfies the Maxwell equation, and that's a stationary solution. What is it? It's actually the electronic part of the Coulomb solution. So that's the W star is actually the potential of the electronic part of the Coulomb solution. So, okay, so that's the wave equation on one forms. Now let's move to linear gravity. That's the very equation we are interested in. And we want to prove that H converges to a linear combination of curve and this stationary solution. So to begin, we use the well-known decomposition. For any solution of linear gravity, it can be decomposed into the curve piece and the regular solution and a deformation tensor. So Km, that's the angular momentum, that's stationary, and it satisfies the harmonic gauge. And K corresponds to the mass perturbation. It's also stationary because curve is stationary, but it doesn't satisfy the harmonic gauge. We are going to fix that. And HRW is the in the solution is the metric perturbation in the regular gauge. So, well, it can be fixed by adding a deformation tensor to the mass change. So instead of K, we get the K star. It still corresponds to the mass change, satisfy the harmonic gauge, but it is not stationary. It actually grows linearly in T, and the leading order is T times pi W star. But anyway, after doing that, the first curve part satisfies the equation, and the equation is linear. So the second part is also satisfy the equation. And compared to the theory we are after, what we're going to do is to argue, well, this piece converge to this guy. Okay, so let's focus on that. It's well known that the regular solution is governed by two quantities, the regular and the Zeru quantity. Both of them satisfy the wave equation. So this part is understood. What about the these w pi part? Well, if there's no regular part, then w, as we discussed, satisfy the wave equation on one form. Now we have, with the presence of this term, well, it comes into the source term. So this is the plan of the proof. First, start with regular and the Zeru equation. Use the wave equation for scalars to argue the case. For the regular equation, that was first done by Laformos, Hosego, and Raniansky. And for the Zeru equation, that was done in the work of Wang, Jordan, and myself, also by Thomas Johnson. Then, just by the algebraic relationship between the regular h and regular gauge and those quantities, we have the decay estimate for HRW. Finally, we repeat what we did for the one form, but take this source term into account. Still, we can manage to show the solution will converge to a multiple of W star. So the decay quantity will be W minus C